Let's get started. Rumor has it, by the way, that a lot of you guys found the midterm to be long. So we're aware of that. Don't worry, we're going to take that into account as we grade it. I can't say much about it because we're actually going to grade it today, so I don't have much to say in terms of the midterm. But come Wednesday, we'll have graded it, and I'll have a better grasp of maybe some of the common problems, and we might do some of the ones that were commonly missed in class if that's helpful. And then I can tell you more about the grading scheme and so on. So, any questions before we start with today's lecture? Yeah, Jersey. I'm sorry, I couldn't hear that. So the next homework we should get out at the start of April. So you should have about 20 days to do it. It's due on April 21st, I think. So today is the 30th, right? So that should be the end of this week, basically. And that'll be your last one. I don't know if we ever announced that in class, but we decided to combine, or basically to get rid of a homework because of all the kind of stuff you have coming up in terms of the project, the little test, the homework, and then the final project. So we decided it was going to be a little bit too packed. Your progress reports are due coming up soon, right? What's that? Sorry? Today. That's right, at 4 p.m. Is that what we said? So I think, yeah, you guys should be submitting those today. And then Viru already sent out an email about the review system, so I think you should have gotten that as well. So after all the projects are in, you'll get assigned three projects to act as a reviewer for. Any other questions? Okay, so this week of lectures is going to be a bit different from the other ones because we're going to be taking more of a kind of high-level perspective on what we saw already and how you would apply it in a particular problem instance. And so we're going to go through a class of problems that we'll call generalized Lasso problems, and we're going to go through and we're going to see what algorithms that we learned so far will have, strengths in certain cases and weaknesses in others. And we're also going to talk a bit about implementation at the end of Wednesday's lecture. Some of the things you should look for when you're actually going to implement, an algorithm, say with the idea of performance as being a key issue in the future in your own research. So it's a bit different. You're not going to learn any new algorithms this week, but I think it's going to be helpful to tie what you've seen together. And then starting next week, we'll start with the advanced lectures, and you'll learn a bunch more algorithms. And that'll basically continue through the end of the course. So I'm pretty excited about this topic because I think it provides provides an avenue for you to see kind of the inner workings of all these algorithms applied to kind of a class of ML problems that is pretty broad. So this week will be probably the most, in a sense, the most ML focused of what you've seen so far because we're really going to be talking about how do these algorithms perform for these particular problems that have statistical properties that we care about. And it's an interesting issue because 3 of the TAs now, I've realized so far, have worked with me on something related to this lecture. So TAs from previous years and this year's, it's made a total of 3. So it's been kind of home brewed in some sense with the optimization staff. So review of last time what we saw. Last time this was the review lecture. We spent maybe the first third or half of the lecture on this big table of algorithms. And, so far, up until this point, we've learned algorithms that kind of fall into 3 classes. First-order methods. Those were gradient descent, subgradient descent, proximal gradient, accelerated proximal gradient. Second-order methods, which we think of as Newton's method being the kind of canonical example, but quasi-Newton methods, are also often called second-order methods. Even though they actually don't use the Hessian, they approximate it. And then interior point methods, which build on second-order methods and extend them so that we can handle constraints by introducing barrier functions. So these three kind of broad classes of algorithms comprise a good part of the core tools in optimization. And in most courses that maybe aren't taught out of an ML department, these might be all that you learn, because really this is a good chunk of the optimization core. And they're a big focus in optimization. Still, there's a lot more out there, and by the time the course is over, we're going to cover some advanced topics that are quite popular among the ML and stats communities, like dual methods, the alternating direction method of multipliers, coordinate descent, proximal and projected Newton. We'll probably get to some advanced stochastic methods. So given the number of tools that are available, not only these core tools, but also the more advanced ones, it may seem overwhelming in a sense to choose a method in practice. And a fair question is how do you know what to use when? And so we've been trying to build intuition all along, that tells us the strengths of first-order methods versus second-order methods and vice versa. And that table you saw last time was a summary of their various properties. It covered the following properties, right? What assumptions on the criterion function do you need to have in order to apply the method? What assumptions do you need to have on the constraints? So either written as functions, being less than or equal to 0, or as sets. How easy is it to implement the method? How do we choose the various parameters that are involved in making the method run? Like backtracking parameters, barrier parameters, step size parameters, etc. And the last two are also very important considerations, and this is where a lot of the methods kind of separate. What is the cost of a single iteration, kind of maybe in a rough sense, for a typical problem? And what are the number of iterations needed before you get an accurate solution, again, for a typical problem? There are a bunch of other important aspects that table didn't cover, like kind of distribute or parallelize the algorithm, which is increasingly important nowadays. What kind of memory does the algorithm require? What kind of memory requirements or data storage issues do you have when running an algorithm on a typical problem instance? And statistical interplay. This last one we didn't cover at all, but it's in an advanced optimization course, maybe after this one, say if you guys were to take 825, depending on who's teaching it, you might learn that a lot of these algorithms they interact with the problem in a statistical way that's interesting. So I'll just give you an example of that. First order methods we know kind of have typically convergence rates that are sublinear, right? They look like 1 over k. For example, under standard assumptions like the gradient is Lipschitz, if I perform k steps with the algorithm, then I expect to be something like 1 over k from the optimal criterion value. There's recent work that says that, well, if you're solving a problem that is an optimization problem that comes from some statistical model, and I didn't care about getting a solution that was any more accurate than the level of noise in the problem, right? So suppose I'm solving some maximum likelihood estimate problem, or maybe a penalized MLE problem, and there was a noise parameter, so I'm observing noisy data, and I didn't care about optimizing below the noise level, right? I wanted an estimate of maybe whatever the parameter of interest is to within the level of noise that I'm observing the problem, because otherwise statistically it doesn't really make sense to get anything more accurate. Well, some recent work says that actually the convergence rates for first order methods in those cases, they're way faster than 1 over k. So 1 over k is kind of it's a worst case rate to get to very accurate solutions, but maybe in a lot of statistical problems I don't actually care about getting a very accurate solution past the level of noise, and so that's a very pessimistic view of first order methods. And there's some work that says they actually get linear convergence even when the function is not strongly convex to within the kind of statistical noise level. So there's a lot of issues that you might have in mind besides these ones when choosing a method in practice, but these ones I think are definitely a good start. And so that table should be a good reference from here on out. What we're doing today is different. We're going to go through particular problem cases and try to see how these various properties come into play, and talk about which methods are applicable and how they may strive or may have trouble in certain problem instances. So the problem instances that we're talking about today, you might call generalized Lasso problems. So they look like a lasso penalty applied to a smooth criterion function. So this might be, a negative log likelihood or some smooth loss function that's convex, depending on the problem scenario, right? Could be like a least squares loss, a logistic loss, something else. And the penalty that we're applying is not the same as a lasso penalty. It maybe only looks superficially different, but it actually is quite different in terms of the algorithmic considerations, which is why we're going to talk about this class. We've composed the L1 norm with a linear transformation of the variable. That's really all the differences. So some people call this analysis regularization. Some people call this generalized Lasso regularization. It goes by a bunch of different names. This matrix D is a penalty matrix that's been given to us. Okay, so either it's been given to us or we choose it depending on the kind of sought properties of the estimate. So the usual lasso you can think of as corresponding to the case from this matrix D is the identity matrix. So that's just going to penalize the pure L1 norm of the coefficients. And that encodes sparsity in the coefficients themselves, right? If we were to solve this problem, say this was a regression problem, so we would take f to be something like a squared error loss, it would encode sparsity in the regression coefficients. The generalized lasso doesn't actually do that, right? It encodes sparsity in d times the coefficients, or d times the estimate. So if we were to write that out as a vector, right, each row I'm just writing out of d here, so d1 through dm are its rows, it encodes sparsity in certain linear combinations of the estimate. And that can result in interesting structure on the estimate depending on the choice of d. Right? So you can think about sparsity in various ways. Think about sparsity in terms of a representation by a basis. So if I just take d to be the identity matrix, right, then clearly its rows look like the canonical basis vectors, e1 through en, right, where ej just has a 1 in the jth component and 0 everywhere else. So I might say that beta is sparse with respect to this basis if when I take the inner product of these basis vectors with beta, most of those inner products are 0. Right, that's just sparsity as we know it, but I'm just saying in a slightly different terminology. Now, we might ask for sparsity with respect to a different basis, right? We might actually doesn't need to be a basis per se. These can actually be linearly dependent. But loosely speaking, we can think of this as maybe a basis for a difference that encodes sparsity in a different manner than the canonical basis vectors. So if beta is sparse with respect to this basis, it means most of these inner products are 0. So it's orthogonal to most of the rows of D. And we'll see that can actually enforce different properties than pure sparsity on the estimate. So here's the outline for today's lecture. Actually, to be honest, both today and Wednesday are going to come from these slides. So there's a ton of slides here. I figured we're just going to go through as much as we can today, and then we'll pick up Wednesday. So we're not going to cover all of this. But we're first going to talk about notable examples of generalized Lasso problems. And this is really going to be pure motivation for the algorithmic considerations that come after that. We'll spend, however long we need to kind of understanding the various problem instances that you might be interested in solving. Then we'll get to algorithmic considerations. So for each one of those problem instances, what are the algorithms that I could apply of the ones we've learned so far? So it should be said that the ones we haven't learned so far, a lot of them can be applied to these problems as well. And after the advanced topics lectures, you may think back to this lecture and see which of those algorithms could I apply. It may be an interesting kind of check to see that you understood a lot of the advanced algorithms. Then we'll go back to the examples, and we'll try to be specific about which ones would succeed and fail. And lastly, we'll talk about some implementation tips, not really just specific to this problem class, but just the idea of implementing code for performance, optimization code for performance in general. So here's the first problem instance that we're going to talk about. And it's sometimes called the fused lasso or total variation denoising, depending on which literature you're reading about it. The fused lasso is what it's called typically in statistics and in ML. Total variation denoising is a name that comes from signal processing. It also appears in ML papers as well, but they really refer to the same problem. And that's when it's the special class of problems where we take D to be a matrix of this form. So it has a -1 and a 1 in each row, and those -1 and 1s fall down in a bidiagonal fashion. Okay, so if I take D times beta, and beta is an n-dimensional vector, then D times beta is going to give me, right, if D is that matrix of pairwise differences, it'll give me the pairwise differences in whatever the input is, beta, right, that's for the fused lasso. And so if I take the L1 norm, I just get the sum of the absolute differences across components. So for this to be meaningful, there has to be some ordering to the components of beta, right? Otherwise, the differences between beta don't make any sense. So we apply this in problems where the ordering between the components is meaningful. And that's why it's called the 1D fused lasso, because we think about the components of beta living on a 1D structure, right? And they are ordered linearly from 1 to n. So we can just see from this that if we want sparsity in D times beta, then that actually means that many of these pairwise differences will be 0, which is different than sparsity in beta itself. Those are different properties. So sparsity in pairwise differences means that many beta I will be equal to beta I plus 1 if D times beta is sparse. Right? So if we were to, say, plot the components of beta along a line, then we would see that the components of beta form a piecewise constant structure if many components of d beta are sparse. Right? Because if many are equal, then we get something that looks like this. They're equal, beta 1 is equal to beta 2 is equal to beta 3, say all the way up to beta 10. And then there's, an inequality, so there's a jump between beta 10 and beta 11, and they're equal for some other stretch of coordinates, and so on and so forth. Right? So like the L1 penalty in the usual sense, we aren't specifying ahead of time where we want these jumps to be with the fused lasso. Right? We're asking it to find these adaptively based on the data. So we're going to solve some problem, we're going to impose this penalty, and the optimization procedure is going to give us back a set of differences that are sparse, where the non-zero differences are going to be, they're going to come out of the algorithm. So here are some examples of where you might apply this type of estimator. Let's suppose that we had a sequence of observations that were observed, say, across time or something, some linear structure, and we'll call those y1 through y100. And we believe that the underlying mean, say, of those observations was piecewise constant. So we're going to then use the Gaussian regression loss, right? So you can think about we're estimating a separate mean parameter for every observation yi we see, but we're going to enforce the penalty on the pairwise differences. So an instance of the fused lasso is going to look like this. Right, where this ends up being my f of beta, and this ends up being my L1 norm of d times beta for particular choices of f and d. Right, so you can see that lambda controls the strength of the penalty. So I just chose some value of lambda for visual purposes here. You can see it does a decent job of kind of estimating the mean in a piecewise constant fashion. The same game could be played, right? The same estimate could be posed with a different loss function. So here I chose the logistic loss. And now I'm actually modeling the mean of y, right? So the mean of y is I'll call pi for the probability that yi is equal to 1 or 0 as a sigmoid function of beta. for each I. And so I'm also enforcing, again, if we enforce beta I to be piecewise constant, that'll also make the fitted probabilities piecewise constant. Right? If two adjacent values of beta I are equal, the same will be true for pi. And so that's all I'm doing here. I'm just changing the loss to be the negative likelihood for this Bernoulli model of observations. And I'm enforcing the coefficients to be piecewise constant. In other words, I'm forcing the means to be piecewise constant across locations. And so this is what I got. Right? It looks like the fitted probability for my first 20 observations is something like 0.7, and then it drops down to something that's a little bit below 0.2, and so on and so forth. Okay, and there's many kind of more complex examples that we could think of with this type of penalty, but we're just going to move on and look at another example, and we'll see later on other applications of the fused lasso. So higher order polynomials are also possible to fit in a piecewise fashion, and those are called trend filtering methods in one dimension. And actually, the very first lecture you saw an example of what we called linear trend filtering. So you can think about it, it's just one step up from the fused lasso, where we go from fitting piecewise constant estimates to piecewise linear estimates. And in trend filtering, we take the matrix D, instead of having a -1 and a 1 in each row, it has 3 entries in each row that are non-zero. And they look like this, 1, -2, and 1. So if I add up the L1 norm of D times beta, I get the sum of the absolute values of beta I minus 2 beta I plus 1 minus beta I plus 2. That's actually a typo. It should say the last term should be a plus. So it should be sum of beta I minus 2 beta I plus 1 plus beta I plus 2. In the first lecture, we gave an example of this, of an estimator that had this penalty, right? And if many of these differences are 0, right? So if the elements of d beta are sparse here, which means that many of these differences are 0, then that means that we have beta I plus 1 is equal to beta I plus 2 over 2. So we have this is true at many locations I if d beta is sparse. For that matrix D here on the slides, and that's called the linear trend filtering operator, or linear trend filtering matrix. And you can continue to go up in terms of polynomial order. The quadratic trend filtering matrix, it now has 4 non-zero elements in each row, and it takes, kind of a higher order linear combination of the coefficients. And if this is 0 at a particular location, you can think about having a quadratic stretch there. Okay? So with these penalty operators, we would also kind of assume some kind of linear structure for the components of beta. And if we were to plot them after we solved a problem with high enough value of the penalty parameter, the first would give a piecewise linear plot for beta, and the second would give a piecewise quadratic plot for beta. So Jersey.
I don't know if this makes sense, but if you wanted to combine the constraints, could you just stack these two D matrices, or if you wanted it to be piecewise quadratic, but also the betas themselves to be sparse, can you stack the identity on top of it?
Yeah, they both make sense, and they're both great suggestions. You could certainly do that. So any combination of these matrices is valid. It's fine. And like you said, let's just think of one example. Let's suppose I wanted an estimate that was either piecewise quadratic or piecewise constant in some parts, but I didn't know where. I just thought whatever the signal I'm observing is going to be piecewise constant at some point, and then it might become smooth. So you're right. I just would stack, we'll call it d constant and d quadratic. Stack the rows together, and I call this, d. And so what's going to happen is that at many locations, I'm going to have, some of these rows being non-zero, and so you can see that because kind of the null space for this one is actually folded into the null space for this one, if anything, if t times a vector is 0, that's going to imply the same thing for this matrix. You can just check that with the way that they're formed. I might get something that's of mixed order. Might look like that or something. So yeah, that's a perfectly valid combination. And really any of the things we talk about today can be combined. Other questions? So some examples of the trend filtering fits are here on this slide. So again, I have an example with Gaussian loss. So now I'm observing a sequence of points, say yi again. Maybe it's over time, or maybe it's over just some ordered predictor. And I want to model its mean, let's say now by beta I. And instead of thinking that the mean should be piecewise constant, suppose I think it should be piecewise linear. Some people call this broken stick regression or segmented regression. It's an old problem in statistics. This is one way to solve that problem, right, without having to figure out ahead of time where the changes in slope should occur. If I just, suppose I'm able to tune lambda appropriately, it'll find the breakpoints for me, and the segmented regression line will just come out of this optimization problem. Okay, so all along this stretch, I have the differences beta I minus 2 beta I plus 1 plus beta I plus 2 equal to 0. Here I have it not equal to 0. So there's a change in slope and so on. And I just gave you another example with a different loss and with the quadratic penalty matrix. I took the loss to be a Poisson loss here. So suppose I'm observing counts, again, across time or maybe across some linearly ordered predictor. And I wanted to model the mean of the counts as, so now for the Poisson case, I'll take the mean, so maybe I'll call mu I, to be e to the beta I. Right, because the mean for a Poisson random variable has to always be non-negative. And if beta I enforce to be piecewise constant across locations, then so will mu I. It'll be the same. And so this is now just the negative log likelihood under that Poisson regression model or Poisson approximation model. And with a suitable choice of lambda, you can see it does a good job of picking out the trend. Okay, so again, if we were to plot the non-zeros of our operator d times beta, we might get a non-zero here, right? Because we can see that this quadratic changes from being concave to convex somewhere around here. And then there's probably another knot down here somewhere, or another non-zero down here somewhere, and so on. Okay. To make things slightly more interesting than the 1D case, we can think about these problems over graphs rather than just over 1D structures. And so the graph is kind of the most arbitrary structure you could imagine. So in this sense, this is a much more general problem. And we'll just talk about the fused lasso over a graph, which is also, like I said, called total variation denoising over a graph in different fields. And in this case, you're given some graph structure over the components of beta. So let's label the nodes 1 through n. Those correspond to components of beta. And either I'm given some graph structure or I build some graph structure over the components of beta that has to do with a particular problem instance. And let's say that the number of edges is m. So I denote the size of the edge set E by m. Then D will be an m by n matrix. And every row of D is going to pick out a pair of nodes that are adjacent in the graph and give us the difference between those nodes when we multiply it by an input vector. Right, so every row of D looks like this. It has all zeros, but it has a -1 and a 1 in some components I and j, as long as I and j are joined by an edge in the graph. Let's think of an undirected graph. So it doesn't matter actually what signs I put here. They just have to have opposite signs. So I have one row for each edge in the graph, and the rows have the locations of non-zeros, and those rows correspond to the two nodes that are joined by that edge. And so if I take the L1 norm of this operator d times beta, then it looks as follows. I get the sum over all edges ij in the graph of beta I minus beta j. So I'm taking graph differences now. This is sometimes, by the way, called the edge incidence matrix of the graph. If you're taking a class on graph theory, this would be the edge incidence matrix or the oriented incidence matrix, either one. So if many of these differences are 0, right, if d beta is sparse for this operator, that means that many nodes in the graph that are adjacent will be assigned the same value. So this is just a, kind of a illustration showing that, if we were to solve some problem over a graph with this penalty on beta, with a high enough value of lambda, we will have picked out nodes that kind of form connected components in the graph that are all assigned the same value. And that's just what these colors are depicting. Each one of these connected components of the graph are being assigned the same value by our optimization procedure. So we can think about beta being piecewise constant over the graph. So here are two examples of this type of penalty applied. The first is an image denoising example. So in this example, my graph is actually just given by joining adjacent pixels in an image. So I have an image here. I forget how big it was. It was maybe something like 200 by 300 pixels. And so I have 200 times 300 nodes in the graph. And each node, which is a pixel here, I join to its neighbors horizontally and vertically. So it has 4 neighbors. The 2 pixels above it and the 2 pixels to its, the 1 pixel above it and below it, and the pixels to the right and left of it. And y, you can think about y as measurements over these pixels. So again, y is 200 times 300 dimensional. And I just take whatever that, the measurements are over these pixels, and I string it out into a big vector. That's what y is. And I'm trying to estimate the mean of those measurements with beta, while enforcing the mean to be piecewise constant over the image. Okay, and I just, for the sake of a visualization, I just assigned each pixel value a color scale. So I created this image, which was gotten by taking a piecewise constant image in reality, and then adding Gaussian noise to it, and plotting it on this color scale so you can see what it looks like. And I solved the fused lasso. We'd call this the 2-dimensional fused lasso, or 2-dimensional total variation denoising. And you can see this is the resulting estimate, beta. Once that long vector beta is then squished back into an image and plotted according to this color scale. It really does pick out kind of piecewise constant components over the image. And visually does an okay job here. So this is not very far off from what people actually do in image denoising. So in image denoising, they wouldn't quite do this, right, because the color scale is not really, it's kind of arbitrary. In image denoising, we would have maybe 3 separate color scales, one for red, blue, and green. So we would measure that according to the actual, saturation value or something in the image. And we do denoising on each of those color channels, and we maybe would group those problems together. But what we would do would really basically reduce to something like this penalty, where we'd enforce nearby pixels to have the same value. So it's not very far off from what people actually do in image denoising. It's just simplified a bit for the purpose of our lecture. Here's another example. I just wanted to show you an example with a non-grid graph. So, in this example, I have the graph that was given to me, right? There's nothing I really could have done in my data analysis. It's just that a 2D grid was the most natural graph for the setting. This is a problem which I don't have a graph, but I have some spatial information, and so I can build a graph. And so in this example, I took crime rates from all of the census tracts in Chicago. And each one of these dotted or colored squares in this image, they have different sizes, right? This one is quite large, this one is quite large. But each one is a proper census tract in Chicago, and I'm plotting their crime rate with a color scale, so that red is the worst, and yellow is the least. There's the least amount of crime. And I built the graph by connecting any 2 tracts that shared a border that were adjacent spatially by an edge. So this is it's a spatially defined graph. It's a planar graph, though, right, because I can plot it. But it's a graph that I just formed based on kind of spatial information. And I ran a very similar problem to what I showed you in the last slide, where I assign a mean to each measurement. So I'm trying to estimate some mean, so maybe the mean crime rate in that census tract. And I'm going to try to enforce it to be piecewise constant over that graph, which means that spatially it has to be kind of contiguous. probably a more proper analysis would treat these as probabilities rather than as real numbers, but just for the sake of an example, I just used the squared error loss. Right? So very rough solution shows us that this is what the denoised estimate looks like. So I can think about each color here being the estimated crime rate in that particular census tract in Chicago. So you can see it really is piecewise constant over the graph. Yeah, Jersey.
So, seeing that on the map, some of those areas are precision data. Could you somehow keep that as part of this by including them in the generalized Lasso penalty part, but not in the Gaussian loss part?
Sure. Why don't we actually? That seems like a good thing to just think about for a second. What would be you could do that, but I claim there's a problem with that. And you can see what the problem is, kind of based on what we know about optimization so far. So let's suppose I were to solve the following problem. So I'm going to only include in the loss census tracts I that were observed. And I'm going to include in the penalty, right, maybe I'll just write it. Yeah, I'll just write it like this, all ij. So there's no restriction here about them being observed, like you said. So that's fine. We can write that down. But I claim that there's actually something that's not desirable about this optimization problem. I actually claim the solution is not unique, just to give the punchline. And you can see it's not unique because this is not necessarily unique. We can't say it's unique for sure. This is not a strictly convex term, right? Because we know that this doesn't have any curvature away from 0. This would be strictly convex if I included all of the observations beta in the sum, but I'm leaving some out. So actually, I don't necessarily have a unique solution for the missing census tracts. So it seems somewhat arbitrary to do this. Would be a whole class of estimates I could assign to the missing observations. But it's a good question. How would I fix this? So suppose you ran into this problem in practice and you want an estimate for the missing tracts. What would you do? How could you strictly convexify the loss? What would be something you'd do? Yeah, we would do something, in practice we would do something kind of cheap, like plus epsilon times the L2 penalty of beta squared for a small epsilon. That would make the loss strictly convex, and so for epsilon small enough, we would think probably this didn't cause too much harm. It would shrink all of the estimates towards 0, but it would give us something unique. That would be a hack to make the solution unique. Good question. All right. So we only have one more example of generalized Lasso problem, kind of a generalized Lasso problem case. We've seen 1D problems with either piecewise constant or polynomial structure. We've seen graph problems with piecewise constant structure. One can actually do graph problems with polynomial structure too. That was actually a paper written by one of your TAs this last year. Yu Shang has a nice paper on that. But I just didn't put that in here because it's a little bit more recent. So now we're going to go to a third problem case, and we'll see each of these now pop up when we talk about algorithms having very different solutions in terms of what algorithm we would choose. A third problem class is a big dense D. So we've seen Ds that are very structured and sparse. Third problem class is when that's not true. D is just dense. When might you encounter that statistically or in an ML problem? So there's kind of two cases you might think of. The first is that if you were designing an experiment and you actually specifically collected measurements that you know should lie mostly orthogonal to whatever the desired statistical estimate is. So it was actually easier for me to measure things that I knew that should be orthogonal to my estimate in some sense, and some kind of sensing experiment. This is typically called an analysis setup, and D is called the analyzing operator. So people study this in signal processing as well. in that case, since the rows of D are measurements, they don't have structure. They don't have some kind of sparse structure. They just come out from whatever my measuring machine is. And if I take enough measurements, because I want to kind of correctly specify the orthogonal, the orthogonal complement to whatever my estimate space is, then I would have a lot of rows, and each row would be dense. So I get a big dense matrix D. Another problem, which fits into this case, is when you put equality constraints on Lasso problems. Right? So suppose I had just a pure L1 penalized problem. This could be a regression or whatever your favorite L1 penalized problem is. And I placed an equality constraint on the coefficients. So I want to solve this subject to A times beta being equal to 0. Well, I can always reparameterize that problem, right? We learned this in the, maybe the second or third lecture. I can always reparameterize an equality constraint optimization problem by expressing the new optimization variable as one that is designed to satisfy this equality constraint, in the sense that if I pick out some matrix D whose columns span the null space of A, and I let beta be equal to D times theta, then by design I will have A times beta equals 0 no matter what theta is, right? Because the columns of D span the null space of A. And so I can reparameterize this problem now in terms of the coefficients that I'm going to take in that linear combination of the columns. So I can minimize over theta, and every instance of beta now I replace by D times theta. And so this would be another smooth loss function in theta, and now you can see that this L1 penalty on the coefficients beta has been transformed into an L1 penalty on D times theta. And because I've just chosen the columns of D to span the null space of A, there's no reason to expect them to have any structure. Right? They may have come from an SVD. It may have come from other maybe clever ways you have of finding the null space. There's no reason to expect that should have structure. It'll just be a big dense matrix. Okay, any questions before we talk about algorithms? Let's take a short break right now. It's a good time to take a break, and we'll come back and talk about all the algorithms applied to these problems. So now we're going to go through our tool set. Our tool set so far includes subgradient method, gradient descent, proximal gradient, Newton's method, and interior point methods. Basically, those algorithms. We're going to go through our tool set. We're going to figure out which ones are applicable to generalized Lasso problems. And we're going to just talk about it now for a generic matrix D. We're not going to think about any structure so far. Just think about D being general. So this is not a smooth criterion, right? So we can't apply gradient descent. We know that already. So we're going to start off with subgradient method as the first thing we learned for non-smooth convex criterions. So how would I apply the subgradient method to this problem? Right? Well, I have to figure out what at every step, suppose I'm at an estimate beta, I want to update it, I have to figure out what the subgradient of my criterion function is, or what is a valid subgradient. Well, the subgradient of this, right, f of beta plus lambda times the L1 norm of D times beta, splits up into a sum of subgradients, according to our rules. The first part is assumed to be smooth, so it only has one subgradient, that's the gradient. So it's just the gradient of the loss function. And this part, what is its subgradient? So you could do this in many ways. One way to do it would be to write out the definition of a subgradient, right? That it's a value that provides an underestimate to the function when I take a first order Taylor expansion. Another way to do it would actually be just to use what is kind of the closest thing to the chain rule for subgradients. It's the composition rule for composing a function with a linear function. And that's what I did here, because we already know what the subgradients of the L1 norm are. Right? The subgradients of the L1 norm are basically just the sign, or anything between -1 and 1 if that thing is 0. And we know that the subgradients, right, if I take the subgradient of, we'll call it g of x, where g of x is equal to f of ax plus b, then the subgradient of g of x is given by taking A transpose subgradients of f evaluated at ax. And so that's all I've done here. So the lambda comes out, it just multiplies everything. The subgradients of this are d transpose times gamma, where gamma is a subgradient of the L1 norm evaluated at d beta. Right, so all I do for gamma is I scan through the components of d times beta. This is a typo here. Each one of these should say d beta in brackets. So gamma I is going to be either equal to, or it's going to be in the set containing the sine of d times beta in the ith component if that whole component is non-zero. Otherwise, anything between minus 1 and 1. Right, this is just the subgradient of the 1 norm evaluated at this argument, d beta. So that was easy enough. Right? All I have to do for the subgradient method is compute the gradient of my loss function. Presumably, that's not too hard. And I have to just look at the current d times beta, which is going to be sparse. Right? Scan through the ones that are non-zero and put the sign in the corresponding component of gamma. For all the other components, I could do anything. I could choose them to be 0. I could choose them to be uniform at random between minus 1 and 1. It doesn't matter. Multiply that by d transpose and multiply that by lambda, and I add that to the gradient. That gives me a subgradient. So that's the upside, that the iterations are cheap. It's not very hard to do that. In fact, we'll use this fact later on, maybe even next time, depending how slow we are. If we actually write out the support of d times beta, then we only have to take very few rows of d when we form this multiplication, d transpose times gamma. Because I can just let gamma be equal to minus 1 and 1 on the support of d times beta and 0 everywhere else. That is a valid subgradient. And if I do that, then I actually have to take a linear combination of a small number of rows, right? Because really, d transpose times gamma is a linear combination of the columns of d transpose or the rows of d. That's all I'm saying. So I only have to remember the rows of d that correspond to non-zero entries when I multiply d times beta. This might be a very small sum if lambda is large enough. That's the upside. I can perform iterations in a cheap way, which is pretty much always true with the subgradient method with a few exceptions. The downside is that convergence is slow. And again, that's normal, right? This is the slowest algorithm that we have to converge. So, it could be a pretty big disadvantage. So we can't apply gradient descent. We already said that. How about proximal gradient descent? Let's try that one, because we have, smooth plus non-smooth. What's the prox operator here? The prox operator, right, is to find the prox of our non-smooth term, which is lambda times the L1 norm of d times z. So we have to solve this problem to evaluate the prox operator. That is not an easy problem to solve for a generic matrix D. Right? When D is the identity, the solution to this problem is soft thresholding. We worked it out on paper. It's very simple to apply. When D is an arbitrary matrix, this problem is no easier than an arbitrary Lasso problem. Right? It's really the same difficulty. I mean, all we've done is we put an arbitrary linear operator here instead of an arbitrary linear operator in front of z in the loss. They're really the same difficulty. And in fact, even when D is structured, so for example, the Gaussian trend filtering problem, where say D had some structure in it, that's exactly of this form. That is not an easy problem to solve. Those all require optimization considerations. So the prox, this is a nice example because the prox is not tractable generically. So we can't really apply proximal gradient descent in this formulation. So let's suppose, again, you ran this problem in your research. You tried to use a prox of something that looked like this. What would you do? So there are various things you could try. One thing you might try is to go back to this problem and reparameterize to make this linear and to introduce inequality constraints in your problem. Right? So I'll just write that out so you know what I'm talking about. I could actually define, right, beta to be equal to, or even say d beta to be equal to, let's call it alpha plus minus alpha minus. And I could solve this problem instead. Minimize overall beta and alpha, f of beta plus lambda times the 1's vector transpose alpha plus alpha minus, subject to d beta being equal to alpha plus minus alpha minus, and each of these guys being bigger than or equal to 0. So all I've done is I've really decomposed d beta into its positive and negative parts. So I've been able to write the L1 norm of d beta as just the sum of the components of alpha plus and alpha minus. Okay, so this is your new problem. Now I can't apply proximal gradient descent because of this inequality constraint. It's going to mess me up. But I could apply an interior point method here. Right? I could log barrier i's, if that's a verb. I could add a log barrier term for each of these constraints to the criterion, and I could proceed with an interior point method. That's one thing you could do. Turns out in this problem that's not necessarily the most efficient route. I really have three sets of variables here, right? I have alpha plus and alpha minus. Each of them are m-dimensional variables, one for each row of D. And I still have beta, because who knows what this term looked like, so I can't really, and who knows if D was invertible and whether I could find it. So it's really not, generically possible to get rid of the beta instance in this term. So I really have n plus 2m variables. So maybe not the greatest idea. We'll have better luck going to the dual, at least in the applications that we saw earlier. And so let's go ahead and do that. In fact, this would be my kind of generic pitch that it's never a bad idea to derive the dual problem for whatever the problems you're looking at, even if you think you have a good approach in the primal. Right? It'll take you some part of your time to do it on paper, if it's possible, and if it's not possible, you'll probably find out pretty soon. And it won't be a waste of your time because you'll have a different perspective. Even if the dual was harder to solve than the primal, it's still not a bad idea to look at it. So what's the generalized Lasso dual problem? I claim it just looks like that. So if we have, f beta plus lambda times the L1 norm of d beta, this is its dual. The variable now is u. U is m-dimensional, so it has one component for every row of D. And the loss function transformed from f to its conjugate, and we're evaluating it at minus d transpose u. And the L1 penalty transformed into an L infinity constraint on u. So let's just go through that. We can probably do that fairly quickly. So I'm going to introduce a variable z for d beta, and I'll rewrite the problem like this. Okay, because we don't have constraints here, and if you try to derive the dual on your own, you would see that it's quite hard to derive the conjugate function of the L1 norm when a transformation is in there. That will give you some trouble. So you're going to substitute in z to get rid of that transformation to make your life easier. That's what I did here. The Lagrangian now, right? It's a function of b, z, and u. It's f of b plus beta plus lambda L1 norm of z plus u transpose d beta minus c. Minimizing this over beta gives us precisely, so I minimize this over beta and z. I get the dual criterion function. You'll see that this term, right, this plus what looks like d transpose u, that whole thing transpose beta, that's like the negative conjugate of f, just by definition of the conjugate of f, evaluated at minus d transpose u. Right, because the conjugate is the maximum of a linear function minus the r function, but here we're doing a minimum of our function minus the linear function. That's why this minus appears on the outside. And why it appears on the inside is that actually we have plus d transpose u transpose beta. Okay, and then this part for the L1 norm, you can look at this and say, well, I'll pull out lambda, and this really just looks like the negative conjugate of the L1 norm. That's all it is. And so we know that the conjugate of the L1 norm is the evaluated at what? It's evaluated at u over lambda. So it's the indicator that u over lambda has infinity norm less than or equal to 1. Or in other words, the indicator that u has infinity norm less than or equal to lambda. And there really is technically a lambda multiplying here, but that doesn't change anything because this is either 0 or infinity. So this is the dual function. And I now just written it equivalently up here as a minimization problem with a constraint. Like this became a constraint. How do we figure out the relationship between beta hat and u? So we're going to try to solve now the dual problem. And we're going to eventually want to recover beta hat. That was the quantity of interest in the, in our statistical problem. So we have to figure out how to link the primal and dual solutions. Well, first of all, we should ask ourselves, does strong duality hold? And the answer is yes, right? Because look, this is a convex problem. It has no constraints, so clearly Slater's condition holds. So in that case, now we can go to the KKT conditions, say for this problem, and we can look at the stationarity conditions to link the primal and the dual solutions. So actually, in fact, this is the Lagrangian, right? We already wrote it down. And we know that if I take a gradient with respect to beta and a subgradient with respect to z, then in either case, those are going to be characterizations for beta and z in terms of u. So let's take it with respect to beta. That's probably the easier one. And we get that the gradient of f evaluated at the solution beta plus the only other appearance of beta is here, so plus d transpose u equals 0. Right? This is the stationarity condition over beta. So it tells us that whatever is the solution, maybe we'll call it u hat, the primal solution, beta hat, that we're interested originally, has to satisfy this equation. Okay, so if we're lucky, this will be an equation that's solvable in beta. For example, if you think back to the least squares loss case, that'll be true here. Think about any of the kind of logistic or Poisson losses, that'll also be true. If you're unlucky, you may not be able to solve this in terms of beta hat. And so when you got to this point, you may say, well, I don't know if it's worth me pursuing the dual because I can't even get the primal solution, even if I had the dual solution. The second relationship comes out of differentiating or taking actually a subgradient with respect to z, right? Because the Lagrange is non-smooth with respect to z. And when we do that, we see that we should have lambda times gamma, say that's a subgradient of the L1 norm with respect to z, minus u is equal to 0. And where gamma is a subgradient of the L1 norm evaluated at z. Remembering that z is equal to d beta over at the solution, we can also write this as, u is in lambda times the subgradient of the L1 norm. Maybe I'll write it like this. X evaluated at x equals d beta. Another characterization for the primal and dual solution. So that tells me that if I ever had a primal solution and I looked at its signs, when I multiply it by d beta hat, has to match essentially the signs of u, where it's non-zero. So u is going to be equal to minus lambda and lambda, the maximum values that it can be, at the points at which d beta hat is either positive or negative, respectively. And if d beta hat in that component is 0, then u can float around anywhere in between minus lambda and lambda. You could also have seen this from the stationarity, from the complementary slackness condition. This would have come out from that as well. So this one doesn't help us really in solving for beta, given that we have u but it's worth writing down anyways because it'll help us later on understand the relationship between the primal and the dual. So now let's go through our tool set, now that we've done that, and think about solving the dual problem. And then we'll hope that we'll be in a case where I can actually, invert this equation for beta and get a solution. So what does proximal gradient descent look like? Well, now it's much better, right? Because the prox operator is to solve, some kind of squared loss problem when I add the non-smooth part. The non-smooth part is just an indicator. It's the indicator that u is less than or equal to lambda, an infinity norm. So I can either add it or I can think about it as a constraint. They're equivalent. So what is this? The prox operator is to find the closest point z to a given point, say u, that has infinity norm less than or equal to lambda. That's just projection onto a box. And you can convince yourself that's quite an easy problem. Right? All that is saying is that I have a box of side length 2 lambda centered at 0, and you give me an arbitrary point and I want to project it onto the box. It's quite easy to do. Let's call z hat the projection. All I do is I scan through the components of u and I see, well, if that component of u is in the box, then I'll just leave it alone. If it's outside the box, then I'll just either force it to be lambda or minus lambda. That's just the projection onto the L infinity ball. So proximal gradient descent is quite straightforward, right? All we do is we take a gradient here, we subtract that times a small step size from u, and then we truncate it in each coordinate to lie between minus lambda and lambda, and we repeat. So it's quite a simple algorithm, provided that we know the conjugate, right? Of course, the caveat is that we have to know the conjugate here, f star. How about in an interior point method here? So this is something you actually did. I think you did this on your homework, if I'm not mistaken. You ran an interior point method, maybe not in this generality. You didn't think about it like this, but really you were doing an interior point method for this type of problem. You guys did a binary image denoising problem. It really was this form, just an example of these problems. And what you did is you took the box constraint that u has to have infinity norm less than or equal to lambda, and I changed that to be a set of linear constraints. Those are equivalent. It has to lie between minus lambda and lambda. And so I just form a log barrier based on these constraints. So I get log of lambda minus ui and log of ui plus lambda for each I. And that's my barrier function, the sum of those after I take the negative. I add that to my criterion. I have a barrier parameter t, and I solve this problem, say, for a small value of t, and then I make t bigger, and I make t bigger, and I make t bigger. That would be our basic interior point method. Right, so the only difference between the barrier method and the primal dual interior point method that you learned from Javier was that do you take 1 Newton step, or do you take as many Newton steps as needed until convergence before you increase t? That's really the superficial difference between the barrier method and primal dual interior point method. So of course the questions are, how efficient are these Newton updates? Right, that's going to determine the efficiency of the interior point method here. So let's just think about that. Let's define the barrier smooth dual criterion function. So this guy here, right, this criterion right here, let's just call f of u. And the Newton updates are going to basically follow the direction h inverse g, where h is the Hessian of f and g is the gradient of f. So we have to ask ourselves, how easy is it to solve a linear system in h? Okay, well, the gradient we can compute just via the chain rule, right, for this part. We just get a d coming out times the gradient of the conjugate evaluated at minus d transpose u, and then this is very easy to differentiate. The log barrier function you can see here is, there are no linear transformations in it. It's very straightforward. What about the Hessian? Well, again, now we can again think about differentiating this. Again, from the chain rule, we get d times the Hessian of the conjugate function evaluated at something, minus d transpose u times d transpose, plus the Hessian of our log barrier term. So what kind of structure does h have? Right, that's going to determine whether it's easy to solve these linear systems or not. Let's look at both terms. look at the second term first, actually. This part is always diagonal for this type of problem, right? Because what we've done, essentially, is that we've moved, in forming the dual, the linear transformation out of the non-smooth part into the smooth part. So the non-smooth part, which is, in this case, written as a constraint, that's going to influence the barrier functions, right, these guys, and they have no linear transformation in them. So that means that their Hessian will be diagonal, the Hessian of this function. Right? It's going to be a very simple matrix that's just given by each diagonal element is given by differentiating this, think of it as a univariate function twice with respect to ui. So that part's always easy, just some diagonal matrix. What about this? This is really going to be where the critical difference is. Well, there's two components here. The first is the Hessian of the conjugate function, and the second is the d and the d transpose on the outside. Right? If the Hessian of the conjugate function is structured, and d and d transpose are structured, then this looks like d times a structured matrix times d transpose, which is still a structured matrix. Right? So let's go to a simple example. If this was diagonal, then this would basically have the same structure as d transpose. And so, in those examples we saw before, d was, banded or had a structure over a graph. That's still fairly structured. So in some cases, we could get lucky. This would be structured, and we could solve these linear systems quickly. In other cases, certainly when d is dense, but even in other cases than that, when the Hessian doesn't have a nice structure, this will not be structured, and so this whole matrix will be dense, H, and it's going to be very expensive to solve these linear systems. Right, so the jury is out for the interior point method. The answer is that it really depends critically on the conjugate loss, whatever that ends up being in our problem, and the penalty matrix. Yeah, Sammy.
Do you have an example of a function whose Hessian is not structured, but the conjugate of Hessian or the conjugate of H is structured? So I'm giving you Hessian is not structured, but
Yeah.
it starts with Hessian is structured.
That's a good question.
Because if they both, if you could say, if the Hessian of vector structure, you could say the Hessian of vector stars are structured. Then this exercise seems a bit, because you might as well do the algorithm on the primary.
Well, interior point method in the primal is not going to be as easy, right? Because we don't have a box constraint. So we'd have to do something like this. So we'd have a ton more variables.
If I consider the constraint version of the primal problem.
Again, that's not going to be, the L1 ball is not a bunch of linear constraints. And so the duality from the L1 and L infinity norm helped us out rewriting those constraints. I can't always take just a non-smooth, function and turn it into linear constraints. But it's a good question, nonetheless. The answer, I guess, is kind of, but you run into other problems. So we'll see that when you have a regressor matrix in the primal, like if I had an X matrix there, if I had predictor variables, then I could form a dual whose Hessian is structured. But I have another problem, which is that I have an equality constraint in the dual that will mess me up. So, I'm not sure I can think of a really good example where if you have a complicated Hessian in the primal, then the dual is all cleaned up. But the problem just lies elsewhere. Okay, so let's put it all together. What do we learn? The primal subgradient method has cheap iterations, and in fact, it's even cheaper if we think about just summing up the rows of D over the active set, S, the set of components of D beta that are non-zero, but the convergence is super slow. Primal proximal gradient involves evaluating a prox that we don't know how to do in general, so it can be very expensive, right? Because maybe I would have to actually go and solve this as a separate optimization problem, which is itself challenging, right? This is one of the problems that we face already. If you had, Gaussian linear trend filtering, primal proximal gradient descent wouldn't make any sense because the prox is the problem. There's no difference between the prox and the original problem. Dual proximal gradient is very cheap. Its iterations involve projecting onto a box, but the convergence we know is kind of medium. It's the first order method. And the dual interior point method has rapid convergence if we could solve the linear systems efficiently, and that depends basically on the conjugate loss in D. So that's the summary. Let's go through one example of a D matrix in each. We'll talk about each algorithm, and then that'll probably be it. We'll continue next time. So let's talk about the linear trend filtering problem. Okay, so suppose I wanted to study linear trend filtering, and I wanted to either fit a Gaussian model, I want to fit the mean in a Gaussian sequence model, or a logistic sequence model, in either of those settings. And other settings work as well, but let's just keep those in mind. Let's suppose further that actually, in addition to just solving the problem, I want a high level of accuracy. Otherwise, when I plot the solution, when I plot my denoise sequence, I see a lot of wiggles. Right? So in this case, there's actually some reason to get an accurate solution. So what algorithm should we use? Well, primal subgradient is out because it's just way too slow. Run subgradient to primal, then to get an accurate solution, I'm going to need a ton of iterations. So it doesn't matter the fact that its iterations are cheap. It's just far too slow. Primal proximal gradient is no different, say, for the Gaussian model. The prox operator is no different than the problem. Right? They both involve solving a penalized least squares problem, where the loss is y minus beta, an alpha norm squared, plus an L1 penalty of d beta. So it doesn't even, that's not really even a plausible route for the Gaussian model. For the logistic model, it doesn't make it any easier. It's still a very hard problem to solve. It just reduces it basically to the Gaussian model. So we don't think about primal proximal gradient as being a real option here. What about the dual algorithms? So you can check that the conjugate has a closed form in both of these cases. So in the Gaussian loss case, this is the conjugate. In the logistic loss case, this is the conjugate. I think this one you did in your homework, the logistic loss case. For a check that you understand where this came from, you can just check that the Gaussian one gives you this as its conjugate. And when you write down this stationarity condition from the KKT conditions, right, wherever we had that, seems to have, oh, here it is. You can check in both cases, I can actually solve explicitly for beta as a function of u. And these are the expressions I get for the primal solutions in terms of dual solutions. Okay, so it's quite easy to find beta once I find the dual solution. So now we're thinking about dual algorithms. Dual proximal gradient is very efficient, right? One matrix multiplication, or two matrix multiplications, and one projection onto a box. That's what each iteration comes out being. But it takes an extremely long time to converge to high accuracy, and this is actually, it especially suffers in this problem because of how poorly conditioned D is. So remember, the convergence of proximal gradient, it is, say, sublinear. It has a rate like 1 over k, or 1 over k squared if we accelerate it. But those convergence rates are affected by the condition number of the Hessian of the smooth part. So what's the smooth part here? It's the conjugate. Its Hessian involves dd transpose. That matrix dd transpose is extremely poorly conditioned if D is this matrix. You can check that its smallest eigenvalue and its biggest eigenvalue are, there's a huge gap between them, which means it's very poorly conditioned. So actually we're in probably one of the most unfavorable settings that we can find for the proximal gradient approach. I've actually just plotted the condition numbers. So this is the ratio of the largest eigenvalue to the smallest eigenvalue for this operator D. And the one you should look at is the red line. This is for 100 points. This is for 5,000 points. It's a log plot on the y-axis, so actually the condition number blows up exponentially, you can see. And you can see the condition number is up to about 10 to the 10 for 5,000 points. Not a very big problem. It's already at 10 to the 10. So if you happen to be, again, encountering this problem in your research, and you take the SVD of this operator and you divide its biggest eigenvalue by its smallest eigenvalue, and you find that your condition numbers are in that range, you're in trouble. That's not a problem that you can solve quickly with first-order methods because the conditioning is just so poor. Let's think about the last one, the interior point method. In both of the logistic and Gaussian loss cases, take a look at these loss functions, the Hessian is diagonal. You can see that directly from here, right? Because there are no terms that depend on both Vi and, say, Vj. It just that are not in opposite terms of the sum. It's just decomposes a sum of terms in each component. So the Hessian is going to be diagonal. D is banded, right? So dd transpose is also banded. So I have D times the diagonal matrix times D transpose for the Hessian, actually plus another diagonal matrix. This came from the log barrier term. So the whole Hessian is nicely structured. It's really just banded. And its bandwidth depends only on the bandwidth of my operator, not on the problem size. Right, so it's going to have bandwidth 5, actually, for this problem. So we know from our lectures, on numerical linear algebra that we can solve banded linear systems very quickly. So this is a very favorable case for the interior point method because each Newton step can be done in linear time. So it's very fast. We also, the Newton steps aren't affected by conditioning, not this in the same way that the first order methods are, because they're transformation, they're affine invariant. And there's rapid convergence because it's a second order method. So basically all of the stars align for interior point methods, and for this problem, it looks like they're the clear winner. Right? It looks like we should definitely use them. And you can see that in practice. You can see a drastic difference between the algorithms. This is actually one of the examples we gave in our very first lecture. I ran 20 iterations of the primal dual interior point method. No, sorry, it's actually the log barrier version of that. It's the barrier method. For a problem with, I think it was 1,000 points, you can see here. And this is the estimate I got. It's nicely piecewise linear. I run 10,000 iterations of proximal gradient on the dual. And this is what I got. And so it's nowhere near piecewise linear. You can see, if you look carefully, there's a bunch of wiggles everywhere. That's because of the really poor conditioning of the D matrix. And if I ran accelerated proximal gradient, I wouldn't really see any difference. It's not going to perform much better. Okay, let's pick up on Wednesday, and we'll come back to other problem cases.